bonus material from section 1.5. My aim in this video is to explain why our horizontal transformations so goofy. And by goofy, I mean if you think of horizontal transformations the way I do, everything is exactly backwards. F of x plus a is a horizontal shift, but it's not adding a to all of the x coordinates, it's subtracting a. Weird. And it's b, that's not what I wanted here, f of b times x. I don't multiply all of the old x values by b, I divide them for some reason by b. And even stranger, when I have multiple horizontal transformations, if I have horizontal shifts and horizontal stretches, I have multiplication and addition. You'd probably think you multiply first and then add to follow the order of operations, but you don't. You even do that backwards. You do this first and this second. My goal is to explain, and it's not easy to do, those three things that are so strange. So I'm going to first try to explain why you subtract a number from the x coordinate here. All right, so let me tell you a little story. Here's a machine right here. This is my squaring machine. So think about it like a physical machine, like a door. And it's this magical door that you walk through this door, and however much money is in your pocket when you walk in, the square of that amount is in your pocket when you walk out. So if you walk into this machine with no money, 0 squared is just 0, you walk out with $0. If you walk into this machine with $1, 1 squared is 1, so the machine doesn't seem so magical again, you walk out with $1. But if you walk into the machine with $2, 2 squared is 4. So you walk out of that machine and now you have $4 in your pocket. So that's pretty cool, this square machine. I'm going to focus really on this point right here. Say you want to have $4, right? You're going to buy something that costs $4. You're going to buy a frosty cold beverage on a hot day and your beverage of choice costs $4. You need to end up with $4. If you're just walking into this machine right here, I'm going to go ahead and give this machine a name. Maybe I'll call it f of x. F of x is my squaring machine, x squared. If you walk into this machine, if you need to make sure you have $4 when you walk out this machine, you better walk in with $2 right there, right? Everyone with me so far? I'm not sure who I'm asking that question to. Okay, now imagine a different scenario. Now imagine a scenario where what my machine does is, let's first do x minus 1. Now imagine you have this machine right here. In words, I can describe this machine like this. It costs you $1 to walk into my machine. All right, that's what this is saying. What this machine does is it first subtracts 1 from the input. So maybe you got $10 in your pocket. Give me 1 if you want to walk in my machine. Okay, here's $1. Now you got $9 in your pocket. You walk through my machine and you end up with 81. All right, so if you start this whole process in blue here, with $10 in your pocket, you'd end up with 81 because you have to pay $1 to get in. That's what this minus 1 right here represents. So in this scenario, you're still thirsty. It's still hot. You still want your beverage right here. You want to walk out of the machine with $4. How much money must you begin with? And you might be like, $2. I'd be like, nope, wrong. Because if you try to walk through this machine with $2, you're going to first pay me $1. Now you only have $1 left. And then if you have $1 left when you walk through this magic machine, 1 squared is 1, you're only going to end up with $1 here. So you don't want to walk in with $2. In fact, you're going to want to walk in with $3. Because if you walk in with $3, you'll pay me 1 just for the privilege of walking up into my machine, which will leave you with $2 in your pocket, and 2 squared is 4. What I'm saying is that if I'm going to sketch in blue a function that on the x-axis I have how much money you begin the scenario with, and on the y-axis how much money you end the scenario with, I am going to want to point at 3, 4 right here. Because if you begin the scenario with $3, you pay somebody $1, that would leave you with $2, and then you'd square that, you'd get $4. The point that I want to make is this function f of x minus 1 goes through this point. And if you run that same analysis on all the other points, what you'd end up seeing is it goes through all of these points as well. It's hard to draw. Let me try my best. Oh, that's ugly. It's ugly. Oh, that's just too bad. I got to do this one more time. All right, this isn't getting any better, so I'm just going to leave it with an ugly graph. The point that I'm trying to make right here is that f of x minus 1 would actually be shifted 1 spot to the right. And the reason it's shifted 1 spot to the right is if you are paying $1, you need to start out with $1 extra in order to end up with the exact same height. So the way you can think about it is, if you want to make these functions have the exact same height, in this one you better start out with $1 extra because you're going to subtract 1 before you even walk into the machine. That's why every point on blue is 1 to the right of the corresponding point in red. And if that explanation makes sense, I think the explanation for these next two cases will be even quicker. Start with the same graph. I have the same cool squaring machine, but now the amount that I charge is kind of strange. What I'm going to do is I'm going to take half the money in your pocket. So if you have $100 in your pocket, you got to give me half of it. You got to give me half of that money, so then you will have exactly half left. So this 1/2 x would represent how much money you have by the time you get to the squaring machine. So in this scenario right here, I'm stealing half the money in your pocket, but I'm giving you the privilege to walk into my squaring machine. You want to walk out with $4. How much do you got to start with? Well, let's see. If I started out with $2, you'd take half of it, so I'd only have $1 left, and 1 squared is 1. That ain't going to work. If I start out with $3, you take half of it, so I got $1.50 left. And I don't know what $1.50 squared is, but it certainly ain't 4. But what if you start with $4? If you start with $4, I'm going to take half of it. That'll leave you with $2. 2 squared is 4. What I'm saying is this point right here will be on my graph. And I'm not shifting everything 2 units to the right, because let's do that analysis and assume that you're buying a cheap beverage. You're buying a non-alcoholic beverage, and your beverage only costs $1. So you only have to walk out of this machine with $1. How much money should you begin the scenario with? Well, let's see. If you begin the scenario with $2, I steal half of your money. That leaves you with $1. Then you walk in my machine. 1 squared is 1. That leaves you right here. You might wonder why you even bothered with the machine. You could have just went and bought 2 of those beverages, but don't get too tied up in the practical realities of this situation. The point that I'm trying to get at right here is that this graph of 1/2 x squared is going to look like this. I'm going to take all the old x coordinates, and I'm not going to multiply the x coordinates by 1/2. I'm going to multiply them by 2. In other words, I'm going to divide them by 1/2. All right, one more example, which I think will shine a little bit more light on these first two. I want to talk about the same weird squaring machine, except now my function, I'm going to go back and reuse g of x, but this is a different g over here. G of x is equal to this. So let's see, if I'm describing this in terms of the machine, you walk into the machine, or you walk into the scenario, you begin the scenario with $X. And then me, because I'm such a nice guy, I'm going to double that. So if you walk into the machine with, or if you begin the scenario with $5, I'm going to give you another 5, so you have 10 total. But to thank me for that, you're going to tip me $3. You're going to give me 3 back. Well, it's getting really confusing. Okay, you're walking into the machine with X, or you're starting the scenario with $X. I'm going to double it for you. I'm standing outside the machine. Before you even walk into the machine, I'm going to double how much money is in your pocket. But then you're going to give me $3 as gratitude. And then you're going to walk up into my machine, and it's going to square how much money is in your pocket. And so my question to you is, you want this $4 beverage. How much money should you begin the scenario with? And that's challenging, right? Try to figure out how much money you should begin the scenario with. You can start talking through it. I don't know, maybe I start with $5. Let's see, double 5 would give me $10, but then I give you 3 back, so that leaves me with $7. And 7 squared is 49. That's way too much money. I only wanted to end up with $4 for some reason. So that didn't work. Okay, so rather than do this guess and check idea, let's think about this a little bit more cleverly. Think about how much money you want to have in your pocket when you walk in the machine. So ignore the fact that I'm going to double your money and that you're going to give me $3 back. After all that stuff happens, you want to walk into the machine with exactly $2 if you're going to want to walk out with $4. So after all this stuff happens, you're still going to start with $X. You don't know what X is. You're going to start out with $X in your pocket, and then I'm going to double it, and then I'm going to take $3 back. And after all that mess happens, you want to end up with $2 in your pocket, because you must have $2 in your pocket when you walk in the machine if you're going to walk out of the machine with $4. So essentially, you need this 2x minus 3 thing to be equal to 2. X here represents how much money you're going to start with. So if you want to know how much money you're going to start with, think about how you would solve for X. you wouldn't first take care of this 2. You'd first take care of this 3 right here. And even though it's a negative 3, you would be adding 3 to both sides of the equation. I know that's really obvious. I know you know how to solve this equation, but think about what you just did. You saw a negative 3 right here, and you subtracted negative 3 from both sides of the equation, aka you added 3 to both sides of the equation. And furthermore, you did that before you even worried about this 2 right here. Order of operations tells you that you do multiplication before subtraction. However, when you're undoing things like this, you first take care of this negative 3. You add 3 to both sides of the equation. Then you divide both sides of the equation by 2. What I'm saying is that if you want to walk out of the machine with exactly $4, if you want to know what point corresponds with this point right here on the red graph, it's the x coordinate that's equal to 5/2. It's this point right here. 5/2 is 2.5. And the reason it's this point right here is because I just solved for x. And the way I solved for x is I first subtracted negative 3 from both sides. So I started at this 2 right here. I started at this x coordinate. And then from this 2, I went all the way over to 5 because I subtracted negative 3. So from this 2, I jumped all the way over to here. Let's show kind of a flow chart. I went over there. I took care of the negative 3 first, and I did so in kind of a backwards way. That brought me all the way over to 5. And then after I took care of the negative 3, I took care of the 2. And I didn't double 5 to get to 10. I cut 5 in half to get back to 250. Because over here, when I was solving for x, I divided both sides of the equation by 2. But note, what I did in terms of the transformations is I took the old x coordinate 5 and divided it by 2 to get 2.5. So really the answer to why are horizontal transformations so goofy? It's this example right here. You really have to think about where you want to end up at, and you're kind of undoing everything to back yourself into that value. So just like when you're solving this equation for x, you see 2 times x minus 3. And you don't worry about the multiplication first, you worry about the subtraction first, which is strange. And you don't subtract 3 from both sides of the equation, you add 3 to both sides of the equation. And then you divide both sides of the equation by 2. Even though it's multiplication here, you divide by 2. That might seem strange. It's not at all strange when you're solving equations. You understand it. That's exactly what's going on with horizontal transformations. And that is why horizontal transformations are so goofy. To be perfectly honest, you probably don't want to worry about any of that. It will behoove you in a section that is this challenging to just kind of memorize this stuff. Memorize these 4 things right here. It'll get you through everything you need with transformations, and it'll be a hell of a lot easier than thinking about things in terms of stretches and compressions and reflections. All you got to remember are these 4 operations and how you apply them.